Thank you. My talk is motivated by two big questions. One question is to understand the black hole information paradox and firewalls. But when I started thinking about this question, I realized that to answer it, one really needs to understand quantum holography. So this is my second motivation. There are some chairs available here. I will try to consider and make a comparison between two kinds of systems. One system is a black hole, and the other kind is a more conventional thermal system. So I want to understand holography in the thermal setting, at finite temperature. And of course, people in this room, many people in this room know a lot about holography, much more than I do. I'm just trying to solve some simple models, ask some simple questions, and maybe find some very naive and primitive understanding. I initially thought about talking about the black hole problem. And for the black hole, one can calculate certain 4-point correlation functions that are also defined for conventional thermal systems, like a bunch of interacting spins. And for the spin system, you can reason qualitatively that there is chaos due to the interactions, and this chaos shows up in the correlation functions. For the black hole, one can actually calculate the correlation function, and there are some peculiar properties, some very precise relations. And the status of my understanding was until a few days ago that there are some holographic conditions I can derive from the black hole calculations. And I didn't know of any example where these holographic conditions are satisfied. And so I tried to actually check one example, which people considered previously. I just formulated it slightly differently. And in the last few days, I was frantically calculating, and as of this morning, I got an answer. I might not have it tomorrow, but I have it today. So I changed the subject a little bit. So it won't be very consistent because it's not well prepared. But if you help me with questions, I would appreciate it. So the first system is a spin system. And let me write a Hamiltonian. I should say from the beginning that it doesn't have exact holographic correspondence, but it's still very similar to black holes. This is the Heisenberg model, and what I want to do is to have each spin talk with many other spins. For simplicity, we may assume that all spins interact with all other spins, and we have this parameter j squared. J is the average coupling, which is defined like this. J squared is equal to sum over k jk squared average. So it's a quench disorder problem. when spin J, this is spin J, when it interacts with many other spins, it's not really important what the distribution function is. And we can solve this problem, at least we can approach this problem in the following way. At finite temperature, spins fluctuate. And the neighbors of J exert some force on J, which is this. It's H sub J. It's sum over K, J, J, K. That's K. And this force in the first approximation is Gaussian because it's a sum of many small terms. And one can write...
So the J's are just taken from some random Gaussian distribution?
Those J's? Yeah. Yes, they're taken from the random...
Infinite, this is just the Edwards Sheridan-Kirkpatrick spin mass?
Yeah, it's like Sheridan-Kirkpatrick, but it's quantum. And this problem has a long history. The first paper, I think, was by Bray and Moore in the 80s, and there were many other papers. And numerically, one can actually solve this problem in the following sense. One can calculate equilibrium correlators in imaginary time. Or
mean field.
Yeah, mean field. And everything I will do today is mean field, but that doesn't mean that it's completely trivial. So this mean field allows us to write average correlators like Sj. Let me drop these upper indices.
That's a question. So
Yeah.
just so we know where you're going.
Yeah.
The original discussion was about these out-of-time ordered correlators
Right.
measuring universal properties of the black hole.
Yeah.
And the point of this model is that it actually exhibits that in a physical system.
It exhibits them to some extent, not exactly.
That's the goal. That's the.
No, that's not the goal. There will be another problem that is almost an exact match to the black hole. So sorry, I'm starting slowly. Maybe I should speed up. But just the general thinking. What happens if we define this function? Then we can write a self-consistency equation because this function defines also the correlator of the fields. And when we solve a single spin in fluctuating Gaussian field, and the field is Gaussian not because the J's are Gaussians, but because there are many small terms in the sum. If we solve this problem in this fluctuating field, we can write a consistency equation and solve it. So for each spin J, the other spins work as a heat bath. Now, there are different heat bath models. One can consider spin chains or spin lattices. This particular model is very nice because one can separate two time scales. One time scale is of the order of J or of the order of temperature at which a spin interacts with other spins. And there is another time scale that is related to the whole system, and there are no intermediate time scales. This is very convenient. Let me switch to the black hole. And the black hole is actually quite similar. It's the Kruskal diagram. This is a singularity. another singularity. We live in this space, and I want to put a mirror using ADS space. So these are classical coordinates U and V, but we can also write the same metric in terms of the usual radial coordinates, and it will be like and something like this. So there is an ADS boundary. One can define fields near the boundary, and this will be O of t and O of 0. And how do we define those fields? We assume that I'm not doing an actual ADS-CFT correspondence here. It's just a semi-classical theory of the black hole. I assume that there is some field phi in the bulk, and we can take the limit of this field as it approaches the boundary. The boundary conditions are 0. The field vanishes, phi vanishes at the boundary. And we can find the asymptotics of the field approaching to the boundary. It will have something like z to the minus delta. And the coefficient in front of z to the minus delta is this boundary field. Now, we can measure various correlators of this field in time. And the heat bath here is the horizon. So there is a past horizon from which some waves are emitted, and the future horizon, all the waves fall in. And if we make a comparison, this site, or maybe its immediate neighborhood, is mapped to all the field modes here. And the bath is something that is defined at the horizon. And potentially it contains many modes because there are Planck scale modes. What questions can we ask about these two systems? One can calculate 2-point correlation functions in both systems. And one can calculate 4-point correlation functions. 2-point correlation functions already show some peculiarity of this particular model that says something about the smoothness of the space near the horizon. It turns out that if we define this correlation function f of t this is the thermal average. And Fourier transform it and take to the -1. Then the result is an analytic function in omega. And it's not true for an arbitrary system. And it is analytic for the following reason. We can relate apparatus at the boundary and apparatus at the horizon by solving the field equation here. The field equation, if you write it in terms of the radial coordinate, is singular at this point. And there is a particular kind of singularity that will give particular poles in the correlation function. But if the function is defined this way, it's f inverse, then all the poles cancel. Just so happens I can explain it later. So if you just solve an arbitrary heat bath problem, you won't find this property. There are usual properties like the retarded green function is analytic in the upper half plane, but not that. So it would be interesting to have more tests of holography, which means the following. This is a special heat bath that is supposed to have a geometric description or something like that. I don't know how to probe space inside, but there is a mathematical way to define fields on the horizon in terms of the boundary fields. And we would like to check that interactions are local at the horizon. And there is a probe of interactions exactly at the horizon. In the black hole case, it's a gravitational interaction that happens at the horizon. In the heat bath, it's slightly more complicated. So let me explain what the probe is. We consider a thermofield double of the system. And the thermofield double, it's just and then we perturb one part of the system and see what happens after some time. In the thermofield double, the two parts have some non-trivial correlations, which are pretty strong. But if we make a tiny perturbation and let the system evolve under a certain Hamiltonian, the Hamiltonian is H double is identity on the complementary system tensor. Maybe I'll put them in the other order. It's our system tensor with identity minus identity on the physical system tensor with H transposed. You will let the system evolve under this Hamiltonian. This state is a fixed point, but any perturbation will grow exponentially in time. And if we calculate the growth of perturbations, we can reduce the perturbations of the thermofield double to perturbations of the thermal state, but the correlators that appear are not time-ordered. They have this form, A of 0. I'll write it backward. And this correlator, if we subtract the trivial term like dB times CA, it grows like 1 over S. S is the entropy of the system, e to the lambda t. Lambda is some growth exponent. And this exponential growth was first discovered by Larkin and Ovchinnikov in 1969. They studied a superconductivity problem, and they were not interested in the thermofield double, but they calculated something for the superconductor in terms of a single electron. And since the superconductor is made out of Cooper pairs, the calculation of some expectation value on an entangled state reduces to the calculation for this thing for a single electron. And more exactly, they found this iterator, P of T, P of 0. P is the momentum of a single electron. And they were calculating the 4-point correlator for the electric current in the superconductor. So they found this, and they asked what that means. And they figured that in the semi-classical limit, if it's just a single particle in a smooth potential, this correlator is related to quantum chaos. So let me just repeat their argument. So instead of this correlator, let's consider just the commutator of two momentum operators. And we may also put J and K if it's a multidimensional system. And in the semi-classical approximation, it's a response function. It's this thing where we assume a classical relations. We have some initial conditions, x of 0, comma p of 0, and we let the system evolve in the space-time, and there is some trajectory in space-time. And then we shift the initial point in x and let the system evolve, and these trajectories will diverge. So this thing characterizes the divergence of trajectories. If the system is chaotic classically, then the divergence will be exponential, but there is a small coefficient in front, h bar. And these correlators will start out with a very small value of the order of h or h squared. It depends on which correlator you consider. You can do this, which is a general expression, but you can, for example, do commutator and anti-commutator. This will be proportional to h bar. Or you can do the commutator and commutator. And this will be proportional to h bar squared. And they start growing like this. After some time, they become large, and the semi-classical approximation breaks. And at this point, the growth stops. And similar thing happens in spin systems. In spin systems, this correlator grows in time, and then it stops. Now, let's discuss how it grows in this case. And there are two parameters, J and the temperature. And first, let's consider this case. J is much smaller than the temperature. It's the high temperature case. Obviously, the dynamics cannot be faster than J. So in general, we expect the growth exponent lambda to be of the order of J. And one can argue, well, using some hand waving actually, how it happens. I can give more detailed argument. I just want to show you all the pieces first. And in this limit, the correlator, it's unlike the semi-classical particle. The correlator of the commutator squared, S alpha of t, S beta of 0 squared average dominates. Is greater or equal than the commutator, the correlator with the commutator and anti-commutator. And that is different from that. Now, if we do the black hole case, the physics of the exponential growth is this. Let's write A of 0, B of t, C of 0, D of t, average. And let's compare it with this thing. So they're different by the commutator in the middle. So this difference is d of t, the commutator minus now, what is this commutator? It's a response function. Again, I'm using the semi-classical picture, and it can be made precise under the usual circumstances when there is a free field, and we work at energies much smaller than the Planck energy. In this case, we're applying C of 0. We hit the system with C of 0, and we're focusing on the commutator. This operator creates some field modes that fall in. And later, at time t, we capture some field modes. And if we just calculate this commutator average, it will be 0, because these two modes are unrelated. And this is related to Huygens argument, which says that regardless of the previous history, the radiation that comes out has very specific correlations. And it doesn't remember about the history. And this is a correct statement if we consider ordinary correlators that have the usual time order. And if we sandwich this operator between two operators at different times, this assumption is no longer true. And what happens is this. This mode C of 0 and this mode that corresponds to B of t meet it near the horizon at very high relative energy. The Lorentz factor is very high. And the Lorentz factor is kappa is the surface gravity. And there will be some gravitational interaction between these two modes. So we can calculate this gravitational interaction. It was done by 't Hooft, but 't Hooft never considered this closed setting when there is a mirror and everything is well defined. So he had an ambitious goal to understand the S matrix of the black hole, which means that a lot of radiation comes in, creates a black hole, and then it evaporates entirely. I don't think his method actually solved the problem, but it solved this little problem of calculating the 4-point correlator. So Hooft wrote something he called an S matrix. I don't think it's a real S matrix, but it's some operator that describes interactions between incoming and outgoing modes. And it has this form. Let me use U, Hooft's U. It's and there will be a double integral we should remember that the black hole is a high-dimensional object. The horizon is a sphere, and points on that sphere are indexed by some angular coordinates. And there is a particle coming at omega prime and a particle that comes out at omega, and they interact. And they interact in this way. There is some interaction function, some energy operator, and I'll write it explicitly later. Now, what is P out and P in?
So,
Yes?
I'm not sure if he ever quite got the right complete story, because this is somehow the leading iconal approximation to gravitational scattering, where you just have some mutual deflection of the particles. But for true high-energy scattering, you expect there to be important corrections to that.
Yeah, that's why I'm saying he didn't solve the complete problem. But let's see. When we calculate this correlator, it grows exponentially like this. And by the way, the exponent is exactly the surface gravity, kappa. And it saturates when this thing becomes order 1. This is only true when T is much greater than kappa to the -1 and much smaller than the scrambling time.
So that's something like when you have a center of mass energy that's Planckian, or the order of Planck energy.
Exactly. Yeah. Yeah. This corresponds to the Planckian energy. However, one can still use the same idea, this thing, to go further and to calculate nonlinear corrections to this exponential growth. Now, when we reach the scrambling time, this thing is of the order 1. We can do the scrambling time plus 3 over kappa, for example, or 5 over kappa. When we reach twice the scrambling time, then fluctuations become extremely strong, and this approximation will certainly break. So somewhere between the scrambling time and twice the scrambling time, it's going to break. I don't know exactly when it happens. But right now I'm interested in the linear regime, meaning it's just a pure exponent. It's like there is some signal and it's amplified in the system before it becomes nonlinear. Maybe I should explain how to derive this formula out of this. Let me define kappa out. We have this past horizon, and any outgoing particle crosses this past horizon. P out is a generator of translation along the past horizon. And physically, it corresponds to virtual shift, fluctuation of space-time, where the space-time above this line shifts a little bit in this direction. And there is a discontinuity, a shock wave. And to write it in terms of the field theory, we just need to integrate the stress energy tensor along the horizon. So P out of omega is integral TUU of U0. Zero means the V coordinate is 0. We're on the past horizon. And similarly, Pn is the integral of the stress energy tensor along this horizon. Now, if you use this U and apply it to B, meaning that if we write this correlator in the interaction representation, B should be replaced by U B of t. In the interaction representation. And when we replace it here, we can at least do the calculation in the first leading order after this replacement, expanding this exponential in the power series. And we get the following answer. We get just a second. It's there will be a pairing between D and B and a pairing between C and A. And here we may use the non-interacting theory. So it's the answer to the first order in the perturbation theory. And times the commutator between B, sorry, it's B, and times IF. And I'm suppressing this angular coordinates. Now, this F is proportional to Newton's constant. This is of the order of the gravitational constant, G Newton. When we calculate this commutator, instead of using B of t and D of t, we can use B of 0 and D of 0, but translate P in time. What does the time translation do to P in? Time translation means stretching in one direction, this direction, and squeezing in the other direction. If we apply the stretching or the squeezing to this operator, it will either increase or decrease exponentially in the logarithm of the stretching factor. And therefore, we can replace this by 0 and multiply by e to the kappa t. And this is an answer in the first order of perturbation theory. Now, I want to emphasize some important properties of this answer. One property is that the growth exponent is exactly kappa, the surface gravity. And we know that kappa is 2 pi over beta. Beta is the inverse temperature. So there is an exact relation between the growth exponent and the temperature. Second, it's not immediately obvious from this formula, but if we compare the correlator between two commutators, or a commutator and anti-commutator, the correlator between two commutators is small. It's second order, whereas this thing appears in the first order. So the correlator of two commutators will appear at a later stage when it's close to saturation. The growth is close to saturation. And another thing which is even less obvious if we just look at this structure, we can try to think what a more general form of this correlator is. And one can think about normal modes that either exponentially increase or decrease. And how do we define decomposition into normal modes? There is something that is evaluated at time 0. The evaluation gives us the amplitude of the normal mode. Then we propagate it and multiply by something evaluated at time t. And it is a similar structure, but you see that here it's a very particular expression at time 0. We take the commutator of B with some operator and multiply by D. One can imagine more general formula for the local expression at time 0 and at time t. If we just assume this expression, not the more general one, this expression meaning the commutator, then one can use the time invariance and the property one can use the time invariance to show that this P in must commute with the density matrix. When P commutes with the density matrix and also grows exponentially in T, this means that the growth exponent is quantized. From these two equations, it follows that kappa is 2 pi over beta times some integer. In the black hole, this integer is 1. I don't know, maybe some more general models. This is the next question. We have certain conditions of kappa being equal to this number and more generally quantized, and the 4-point correlator having this expansion into normal modes. There is just one normal mode in this expansion. With local expressions given by this form, can we find some spin model or a similar many-body problem with these properties?
Just one small confusion. So it's n times, and then what's the dimensional quantity? So kappa is 2 pi. Oh, times n.
Yeah, kappa is 2 pi divided by beta.
Times n. Okay.
Times n. Yeah. And it turns out that there is such a problem, not the spin problem. There are several problems that are described by the same equation. And originally, there was a paper by Kitaev and A. It was in 1990s. They considered an SUN magnet when n is large. And their problem was that the spin is in some representation of SUN. It can be either symmetric or antisymmetric power of the fundamental representation. This power is greater than 1, much greater than 1, but much smaller than n. And under this assumption, one can write a self-consistency equation and solve it. And detailed calculation were done by Parcolet and Georges in about 1999, I think. And actually, many people, including Kitaev, advertised this model as an example of quantum holography, but they didn't have exact criteria to check on that model. It turns out that this model satisfies my criteria, which is the analyticity of the inverse correlation function and the growth exponent and the structure of the commutator. And in fact, to find this this thing, I'll show you the model in a moment, but what I did is this. I wrote a kinetic equation for this 4-point correlator. Of course, kinetic equations are difficult to solve, but I just guessed this form of the solution. It worked. So just plugged in this formula where Pn was the energy momentum tensor on the horizon, which is deduced using the 2-point correlation function. So what we do is we know the boundary correlator. We expand it to the product of a retarded and advanced response part that is analytic in the upper half plane and the lower half plane. And these advanced and retarded responses correspond to the propagation between the horizon and the boundary. And when we propagate back to the horizon, we can define this Pn, and this way we can guess the solution. So let me just talk about this model. It won't be the SUN spin glass. The model I want to show you, I call the random quartic model. It's this. Not that it matters, but there is a finite combinatorial coefficient to make calculations convenient. So there is a bunch of real fermions, Majorana operators. C sub j is a Majorana operator. And they interact in groups of 4. But these interactions can involve any combinations of four sites. It's a hypergraph of order 4. And we define the effective coupling like before. And
And the J's are Gaussian.
it doesn't matter if there are many interactions. Yeah, right. It can be plus minus 1, something like that.
The short range, right? I mean, there is no any long range.
No,
I mean, the distribution, the Lorentzian distribution would not be good, but.
I mean, in terms of separation of sites.
Oh no, it's long range. It's long range. We take any combination of 4 sites and include this interaction.
it's infinite.
Infinite range, yeah, infinite range.
So there is some normalization, so that the sum is fine.
There are n sites. N is a big parameter.
You have in J squared, there's a 1 over n.
Yeah. J squared is proportional to 1 over n cubed. So.
N cubed.
Yeah. So J K L M. Well, maybe I should write it this way. But it's not important that they all interact. We can have n sites and 10 times n terms, a large constant times n terms. We just throw those terms randomly into the system, and they just
C's set are anti-conditional?
yeah, the C's are Majorana operators. Now, we can use a mean field theory to solve this problem. We can define C either using real time or imaginary time. For example, if we do the imaginary time, it's the convenient normalization is -1/2, and I'll call it g of t. Now, we can have some diagrams like this. There is a loop corresponding to one site. It's, say, site J, and this is also J. And at each point in this loop is the imaginary time. At each point, this interaction may occur, and a single interaction won't have any effect on the partition function because the distribution is symmetric. But if we consider two such terms at different times, this vertex is parameterized by times tau prime. This site interacts with three other sites. And so we can draw a diagram like this. And for self-consistency, the green function of each of the other three sites includes diagrams of the same form. And this includes diagrams of the same form, and so on. And this amounts to some equations for the green function. So one equation is the Dyson equation.
Is each of those blobs two vertices? Is that, I mean,
each of these blobs are two vertices.
Why are they drawn together as opposed to pulling it apart into like a sunrise graph?
Yeah, you can draw them this way. It's a dual picture. Yeah. So you can draw them this and.
Yeah, good. I mean, these iterated rainbows came up before as a model of a black hole in Han Liu's work. We can talk about it later.
Okay, yeah. But the first reference I found was Sajdev in year 1992, something like that. So I omega n minus. And now I should be careful. There is some coefficient in front. I think it's j squared over 6 minus sign. And this corresponds to this. And one can solve these equations. in practice, one solves it in the limit t much smaller than j. First, if we take t equal to 0, then g of I omega is minus I. Just a second. Trying to remember some factor which I don't remember, of course, but it's proportional to omega to the minus 1/2. If t is not 0, and this solution was obtained, the first solution was by Sajdev and Ye, the second solution at finite t by Parcolet and Georges. It's basically sine don't remember. Anyway, it's something like this. Some coefficient in front. But the important thing is 1 over the square root of sinh. And you can also do it. Sorry, no. This should be. Sorry, this should be done in real time. And this sinh of the real time tau over beta. And if you do it in imaginary, if you do it in the frequency domain, you get some gamma functions. Now, there is a complete solution. How do you find this 4-point correlator? The 4-point correlator is also mean field. Imagine the following. Suppose it's not this complicated system, just a classical ferromagnet with many interacting spins, infinite range. There is a local susceptibility and global susceptibility. A local susceptibility means that you apply some field locally, and it doesn't matter. Since you are not acting on other spins, you just assume interaction with the heat bath. Now, if we apply the same interaction to all the spins, then there will be a power series. It will be in terms of these diagrams, I drew this diagram specifically for this purpose, not in the traditional form, but in this bubble form, because now this expansion corresponds to and this chain will continue. Now, we should be careful about the type of the green function, because we can no longer use the imaginary time green function. What we have to do is this. we have real time t. Sorry, maybe I should still use the horizontal axis for t. It's the real part of t and imaginary part of t. And if we calculate ordinary correlators like time going up, 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 and then down, 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 this is done on the Keldysh-Schwinger contour. So the Keldysh-Schwinger contour goes like this, from 0 to minus beta, and then it goes this way and that way. The other way. In this case, we cannot accommodate this out-of-time order correlator, and we have to double the Schwinger contour, the Schwinger-Keldysh contour. We have to do this. And we put two operators at greater times. They were B of t and d of t prime at these 2 points, and we put two other operators at those 2 points. Maybe it should be so there are 4 times involved, 2 times here and 2 times there. Since we're interested in the regime when the separation is sufficiently large, not very large, but sufficiently large, we can forget about the initial conditions and write a kinetic equation, mean the asymptotic regime when t and t prime go to infinity. And then we write this growth as an integral equation in 2 variables, t and t prime, with the kernel described by this bubble. Let me write the kernel more exactly. The kernel is this. It's t. Let me flip the picture. It's better to multiply matrices right to left, because this time I'm used to doing this. It's t prime. For this, let me use tau prime, and there is some interaction going on here, and this interaction involves 2 loops. So this is the retarded Grange function. This is the retarded Grange function, and that thing is that is not a green function. It's actually a correlator without any time ordering. It's f of tau prime squared, because there are 2 bubbles attached to this. And so this is done. It's better done in the frequency representation. And this part of the kernel is better done in the time representation. And we'll look for a solution that grows exponentially in time. So the ansatz for a solution is Um, okay. And this is K. So this is the kinetic equation, and we need to guess the solution. This will be an educated guess using the black hole solution. So let me draw this picture. This is the horizon. And this is the mirror. And the signal propagates from the horizon to the mirror and back. And the correlation function on the mirror and on the horizon are related. These are related by some asymptotic coefficients, C of omega star. So the signal near the horizon is C of omega times the signal at the boundary. And in particular, A of omega, this is the spectral density, which is defined by it should be the anti-commutator. I'm sorry for doing this very technical thing. I'm excited that I guessed the solution correctly and make you suffer. Oh, sorry. But anyway, let me just say it in a few words. When we have this function, it has analytic and part that is analytic in the upper half plane and in the upper half plane. And these two parts are exactly C and C omega star. So A, this function is proportional 1 over C what we have to do to find the solution, we take the correlator at the boundary, split it into C omega and C omega star, and then we need to include this exponentially growing factor, which is on the horizon is very simple. It's just multiplying by this exponential, because on the horizon the fields are local. And in terms of A, we need to shift this omega plus lambda over 2 and that omega by lambda minus over 2. So we just take it times I.
Wait, what's lambda again?
Lambda is the growth exponent here. It's just an ansatz.
Which is not us.
Yeah, but again, from the black hole discussion, we know that lambda should be the same as the surface gravity, which is 2 pi over beta. We just use this, plug into that, substitute into the equation, and it works.
It doesn't depend on the coupling, the strength of the coupling, somehow?
It's strong coupling because the coupling is the ratio between these two numbers.
Just strong.
Yeah, just strong.
Yeah. Good. Wow.
Yeah.
The same value of, just in terms of the temperature.
Yeah, because once you assume strong coupling, there is no free parameter anymore. It's just a certain limit.
Is this sort of like a viscosity bound where you
Maybe.
kind of a maximum to the top? There's a maximum to how fast, how big the alpha is?
Probably. Yeah, probably. It seems to be the same flavor. Mm-hmm. Okay, that's it. Thank you for your attention.
You said that somewhere in here you were going to assume that the spin was in a representation that was large but small compared to n?
Yeah.
Where did that come into this analysis?
Well, imagine that first we have complex fermions rather than real fermions. Then we have spins, and each spin is n fermions. Real fermions, but the occupation number is low compared to n. Actually, Sajdev considered an arbitrary occupation number, and they also considered a bosonic model. But for finite temperature, it's not easy to find an exact solution in that case. When the occupation number is low, then there is an exact solution. They found an exact solution at exactly 0 temperature, but not at finite temperature. So it's basically a similar model when you put these things and you say that J and L belong to one blob and K and M belong to the other blob. And these blobs are models for spins, SUN spins. So it's basically the same model.
So I don't see how that kind of assumption has an analog in the holographic setting. Am I missing something, or do you think that this phenomenon may be more general and may not? I mean, as you say, you need this assumption to get an exact solution. But do you think that this exponential growth hierarchy, the correlators, could be more general?
I don't know. I still don't understand why we get an exact solution. But what I was looking for, and this calculation seems to confirm this. It's a map, a holographic map between two surfaces, not between the bulk and boundary, but between the boundary of the space and the horizon. In this case, we can imagine that something more complicated happens, and that would correspond to scattering, which means that waves do not propagate between the horizon and the boundary freely, but they scatter in the middle, and something messy happens. But I don't know exactly what it means. I guess the next step is to consider small perturbations to this model, because this model is simple. One can probably handle perturbations, and then we'll see.
So the operators P in and P out that are defined as translations along U and B.
Yeah.
And then those two axes are characterized by the fact that there's an analyticity in the upper and lower planes of the two-point function.
Yeah.
Could you try to define those operators in general thermal systems that have the KMS condition?
KMS, what is KMS?
So there's a periodicity, the imaginary time axis of the two-point function, and there's an analyticity. Right, it's analytic in this strip in the imaginary that has a finite width.
Yeah, of course. You can always do this. You can always decompose a function, assuming that it doesn't vanish on the real axis. You can decompose it into a product. One part is analytic in the upper half plane, the other is analytic in the lower half plane. And even you can do it in a matrix form.
So then, where do these holographic systems and non-holographic systems diverge? It seems like if you can define those operators for any thermal system, you can go through with this calculation. And where can I see that the two kinds of systems diverge?
Right. In general, C of omega will be analytic in the upper half plane, and this will be analytic in the lower half plane. What happens if we extend C star in the upper half plane? In general, there may be arbitrary bad singularities. For a holographic system, there will be poles at exact locations, omega equal to omega n, the Matsubara frequency. At the Matsubara frequencies, there will be poles. At the worst case, it's a single pole at each point, omega n. When you modify this function, it's the spectral density, but you can, instead of the commutator, you can just consider the correlator and call it F. This corresponds to the multiplication by a certain factor. It's the Fermi factor. 1 over e to the omega over t plus 1. And this factor has zeros at the same places as the previous function has poles, and they cancel. So if we use the decomposition of this function instead of the spectral density, there will be no singularity at all. But I should emphasize, we should consider the inverse of the function. So these coefficients are in denominators. They still may have zeros, which will give poles in F omega, which corresponds to decaying modes, because we usually have decaying modes. It's a pole at imaginary frequency. But F omega has no zeros at all. That is unusual.
So you're saying what's special to holographic systems is the cancellation between poles?
Well, probably, yeah, it's the cancellation. The spectral density has poles or zeros. Sorry, it's the inverse spectral density has poles. The spectral density has zeros at certain locations.
So what would you get if it wasn't a holographic theory? If you
we could have zeros anywhere. Actually, I don't know, but there is no general reason why the zeros be restricted to those numbers.
Can I see you state again in physical terms, what is the instability in this exponential growth in time you discussed at the beginning? Were you saying that was coming from the thermal field double Hamiltonian having a minus sign in one half?
Yeah, exactly.
It's chaos. I mean, it's chaos.
Yeah.
It's basically chaos is what it is, right?
Yeah.
I mean, the whole point is that this system is chaotic. That small initial changes become large. That become large differences after time order of order 1. That's what that looked at.
But so this is a time of you were arguing for that in looking at the interaction perturbation of like the pre-vacuum state or something like that, the pre-thermal state. Then you introduced the interaction, and that led to the instability. Is that what you were saying?
Free thermal state. In the thermal state, you don't see the instability. You need the thermophile double.
So which state was the unstable state?
The thermophile double.
But that is the thermal state.
No, it's related to the thermal state. The thermophile double, it's an entangled state of two systems. Right. And they evolve in sync. Basically, they rotate in the opposite directions at the same speed. Okay. If you perturb one system, they start rotating completely out of sync. So you lose correlations between the two subsystems.
Right, but since the thermophile double is not the physical system, well, actually in this case it could be if you have an internal black hole, but what's the physical implication for like observables outside the horizon of this phenomenon?
I don't know. It's nearly impossible to measure this out-of-order correlators. So there is no direct physical implication. But it's a probe of interactions exactly at the horizon. I don't know how to formulate it in different terms.
So black holes, they have these quasi-normal frequencies that we're familiar with, which represent the decay to equilibrium. And they're in the same order as this, but they measure something different. And the interesting thing is, the black hole has this famous redshift at the horizon, which is exponential decay, which is not in any of the quasi-normal frequencies. But this is a physical thing which is directly related to that redshift. And it is, it's that if you make a small perturbation on the system, any small perturbation, it's chaos. It's how large that becomes as compared to the original unperturbed state after some amount of time. So this kind of missing
unperturbed mixed state.
Yeah. So it kind of closes off this circle of what was the relation to quasi-normal modes and the gravitational redshift. They're different things. But, yeah.